I would like to welcome you on behalf of Royal Circuit Solutions and Advanced Assembly to the second part of Chris Hunrath's presentation on flexible PCB design and stack-ups. Chris joined us last week along with Bob Meyer of Royal Circuits, where we learned a great deal. And if you get a chance, again, go to our blog, royalcircuits.com, click on the blog link, and you can find a recording of that first presentation. Today's presentation will also be recorded and will be available to you within 2 business days, along with a copy of Chris's slides. With that, let me introduce the really encyclopedic Chris Brown. This guy's got a knowledge of just about everything. Chris, would you like to tell us a little bit about your history and what you do with Insulectro?
Sure. So I've been with Insulectro almost 20 years now. Been in the industry since 1983. I've done a number of webinars for many of my customers, several for Royal Circuits. So if some of you have heard this before about me, I apologize. Started in multi-wire, which was a very interesting technology where we actually melted polyamide coated magnet wire into dielectric films and then drilled and plated them just like traditional PCB. That's how I got started in this business. Learned a lot about electroless copper from some of the pioneers, some of the folks that worked in the circuit board industry all the way back to the 40s, and just been involved in printed circuit boards, both from the manufacturing side, the chemistry side, and the materials side, ever since. So this is my passion. I consider myself a material science geek when it comes to electronic materials, and I'm grateful for the opportunity from Royal Circuits to be able to present to the folks on the call today.
Oh no, the pleasure is certainly all of ours, Chris. Really great having you. And hopefully joining us here is Bob Meyer. Bob's experiencing a little bit of technological trouble today, but Bob, if you are there, can you tell us a little bit about your background and what you do for Royal?
Yeah, Mark. I've been in the printed circuit boards for about 40 years. Kind of worked into the flex side of the business. Been doing, started with Royal a little over 3 years ago. Brought the knowledge I had when they were looking to upgrade the facility to more advanced circuitry and rigid flex and those type of products. So taking the experience that I have and bringing in some other engineers and people familiar with this flex and rigid flex, we've been moving to a much higher end flex and much quicker turnaround times and building much more complicated boards. And we're progressing, weekly, monthly, getting a little better, adding equipment and growing the company that way.
All right. Together, these are 2 of the smartest men that I know when it comes to flex PCB manufacturing. So we're really grateful to have you both here today. With that, let me go ahead and turn it over to Chris and Bob, and you can tell us a little bit about Royal Flex and then tell us about Flex Circuits. It's all yours.
Yeah, so Bob just put up a slide on Royal Flex Circuits. Why don't you go ahead and just say a little bit something about Royal Flex?
Excuse me, Chris, I cut off there.
Yeah, no worries.
Okay.
All right, I'll jump on that one while we're letting Bob get his laptop reconfigured there. So Royal Flex Circuits is one of the premier quick-turn PCB fabricators in Southern California. The facilities, I think it was November, wasn't it, Chris, that we opened up the latest factory down there?
Okay, I'm back on, Mark. Yeah, we've been in this facility for a year, a little over a year. January of 2019 is when we moved in, right on the 1st. So we've been here about going on almost a year and a half. We expanded by about 10,000 feet over our last facility. And what this has really helped is this was custom designed from the warehouse up. So we got to lay the factory out the way we wanted for equipment and processes and for future growth. And that's where we've been right now, and adding equipment to make, the higher end PCBs, the more exotic materials. We've added, high temp pressing, which is getting more and more prevalent. seeing, you know, finer lines, you know, hybrid combinations, looking for the high speed flex and that type of product, which Chris will go over later. But we're a lot more dynamic than we were 3 years ago. So, and we continue to build a new product where we generally don't shy away from things just because we haven't built it. We look to see if we can, you know, find answers and resources for our customers to get their product to market.
Yeah, actually, I think, Bob, you pretty much covered this, so I'll continue on.
Okay.
So just a little bit about Insulectro. We're an electronic material supplier. We supply rigid, flex, printed electronic, metal foils, and a lot of the products that go into making both rigid and flex PCBs. Our business is really mostly electronics based. In other words, all of our materials either are used for the manufacturing of electronic components and devices, and we're doing more and more with printed electronics and flex. I'm going to go through some of the new materials today, but by no means can I cover everything in the hour that we have. So certainly if you have questions about electronic materials, don't hesitate to reach out to you know, folks like Bob or myself, and we'll try and get answers for you. One of the benefits of Insulectro is we can stock a lot of different products for a lot of different customers. So folks like Royal Flex, they don't have to have everything on their shelves because there are so many different part numbers with copper combinations, thicknesses, resin systems, material types. So that's one of the things that we bring to the U.S. PCB industry.
And to build on that, Chris, we bring in a lot of the standard products, so the quicker turns will have a lot of different. But the minute you get to an odd based copper, then you know, like a half over quarters and things like that. Then that is what Insulectro does a good job at you know, getting for us in timely fashion, things like that are a little more unique to each design. So.
Yeah, a lot of will call, a lot of same day turns. So,
right.
And we're always looking at the business, trying to do a better job because we believe that brings a lot of value to folks like Royal Flex and their customers in having the right materials available. Just a snapshot. I presented this slide last week for the folks that were on last week's webinar. We were going over the materials more. Today, we're going to go over into some of the new materials, but also stack-ups and design considerations. But you can see just when it comes to electronics, a lot of different shapes and a lot of different materials involved. Everything from conductive inks, which you see on the right-hand side, to rigid backplanes, to flex, to printed electronics, membrane, touch switch. There's just a lot of different areas and aspects of the technology, sometimes combined. You know, rigid flex is something that continues to grow. And of course, why flex? And flex is used in all kinds of things. It's used for you know, things in motion. It's used for form factor. In other words, fitting a lot of circuitry into a tight space and being able to fold it up. It's been used in aerospace, outer space. It's finding applications in automotive. And one of the areas that has a lot of growth is medical applications, both for form factor and for flexibility. Great example of form factor, where you can take, in the upper left, you can take a circuit like that, populate it, and then fold it up into a much tighter package. And then in the middle, you can see where, you know, flex is just a much cleaner way, much more reliable way than using wires from a rigid PCB to connectors.
Yeah, it takes a lot of that hand wiring and the old kind of pin, you know, put pins in and wrap the cables and things like that, right? Much more reliable for sure.
Yeah, and it also saves weight. It can save weight, it can save cost, and all the manual operations involved.
Right. And it's fully tested prior to assembly, where the cable assemblies are a little more challenging.
So one of the goals that we have with this is to make the design more successful from the start. PCBs are becoming more and more an integral part of the design. Not that they weren't always, but what's happening now is with higher speed circuitry, you have to consider the transmission lines between connectors and components and the like. And again, another goal is here today is to introduce ourselves and, you know, basically set us up as a resource. You don't need to be a material science expert. You can call on us, you know, the Royal Circuits folks, as well as myself, and we can help, you know, bring the right material to your design. So there's a lot of different design considerations when building flex. By the way, this is a review from last week. So again, folks that were on last week, I promise there's new content coming up. But I just thought it was important for people who attended this week versus last week. These are some of the things you consider in a flex design. You know, certainly bend and install versus occasional flex versus dynamic flex. Those are very important factors in how you would set up the layers and also the you know, the overall geometry of the you know, of the circuit. Electrical speed, frequency, bit rate, high current, high voltage. I've seen some very interesting applications where people need a high voltage. A great example is some flex circuitry that's used in battery arrays for electric vehicles. And then of course the RF applications, ways to manage noise, electromagnetic environment. Certainly from a design standpoint, if you don't design things correctly, you can either be a source of noise or susceptible to noise or electromagnetic radiation. And those are things that, you know, that can be managed in the flex design. Of course, operating temperature, and going back to the cable versus flex design, with the new HT material, which I'll talk more about, you can replace high temperature cables now with a material called HT and actually make a flex circuit that will survive operating temperatures at 500 degrees. And that's the operating temperature, not the you know, the peak assembly temperature. And then of course, use environment. Is it indoor or outdoor in a environmentally controlled place, or is it going to be someplace that's under you know, under some sort of environmental influence? That could be everything from moisture to radiation. Just again, some more of the overview is the general flex types. You know, you have your basic single-sided flex, double-sided flex. Still a lot of double-sided flex manufacturer out there. Multi-layer flex, and then of course rigid flex. A lot of rigid flex designs, and we'll talk some more about those stack-ups.
Hey, Chris,
yes.
real quick, while we're going through that, if you have any questions as we go, feel free to answer them in the question and answer form, guys. We're happy to stop our presenters at any time and try to get your issues addressed now or at the end of the webinar.
Just a small point, and one of the goals that we have today in this webinar is you don't always have to do a rigid flex. It's of course very important because of soldered components and surface finishes that the areas where components go be as rigid as possible. So one solution is to add a stiffener, a lot less expensive than making a rigid flex board. So I'm sure many folks are already aware of this, but just wanted to make a point that, you know, this is where Royal Flex, the design folks there, are good at suggesting things to keep the cost down and to get the functionality you need. So this is an example of a stiffener on a pure flex build where you don't need to use a rigid flex. Now, if you're doing a strip line construction for high frequency and you're looking to put on a connector in the rigid portion, you may want to have a rigid flex versus a stiffener system because the interconnect structure is a lot more complex doing it the other way. Again, that's why you can consult with the Royal Flex team, and they can help you through those kinds of decisions.
So Chris, first question we've got is, what's the technical difference between a rigid flex and a flex with stiffeners?
So rigid flex has the circuitry integrated between the flex portion and the rigid portion, and that's done with plated through holes. A stiffener is just that. It is a rigid material that's bonded but not electrically integrated into the flex circuit. So hopefully that makes sense. The stiffener, flex board with a stiffener is a much simpler manufacturing process than a rigid flex. So my suggestion would be is use a stiffener when possible, but there are cases where you have to have a rigid flex where the rigid portion is electrically integrated into the into the flex area.
Yeah, or if, like you said, you have a component that needs a lot more strength, so you need those holes plated through the part just in order to get that extra thickness. I mean, there's times we actually even put stiffeners on rigid flex, right, in order to help insulate or even create a even stronger area to mount into the chassis and different items. So they're used quite a bit.
Okay, we've generated several more questions on that line, but I'm going to hold most of those until the end. Please continue, guys.
Okay, so just an overview of some of the flex building blocks. In the top area, you have your polyamide clads. Now, the technology has evolved over the years, where polyamide can be directly bonded to copper foil. In previous years, there was an intermediate, usually acrylic, and by and large, the direct bond polyamide is the way to go in most applications. It's not that you're not going to use acrylic adhesive as part of the structure, and I'll talk a little bit more about the advantages and disadvantages of using the acrylic layers. But that's pretty much taken over the industry. Again, this is some of the review from last week. You know that these are the building blocks. Just a review here, and again, these slides are going to become available. But for those not familiar, these are the IPC specs. I'm sure many of the folks on this webinar are already familiar with these, but this is just the IPC specs for flex and what they cover. And of course, just to note, IPC 6012 is for rigid and 6013 is for flex. Those are the fabbed PCBs. And then the materials have their individual specs as well as the metal foils. And just an overview of film types. So AP, AG, and AC are all polyamide systems. And some of the things I've talked about last week, I pulled out of this slide because this is more on the design and stack up part. But polyamide systems, polyamide is a very high temperature resin system. It's what we call an addition polymer. It makes solder assembly possible on a flexible film, whereas things like polyester films or PET films, you can't do normal assembly on them. Yes, there are some systems that can use low temperature solder, and you can do some assembly on polyester films, but polyamide is king when it comes to processing and doing full assembly on a film-based system. It also has low loss properties. It has a lot of desirable properties, and that's why it's become pretty much the go-to material for flex. And then, of course, you have the acrylic systems. Those are the building blocks or the components that allow you to put the building blocks together to make multi-layer systems. We have the new GPL material, which I'll talk more about in coming slides. And then there's HT and TK. These are the high temperature lamination materials. They certainly have a place in particular designs. Whereas the LF and FR acrylic, they're the easiest to use, the most common, most cost effective. But there's certainly applications where you want to use the other materials. And again, that's part of what today is about. Just an overview of some of the electrical properties. I'm not going to go through all this, but this is available to the folks, you know, on the webinar. Everything from glass transition temperature to its dielectric properties in both dielectric constant and loss tangent. So one of the things that that applies to flex, and even more so a rigid flex design, is the electrical performance characteristics of the traces that travel between the two rigid portions. And many PCB fabs now are working with low loss materials. It's not just FR4 anymore when it comes to building the PCBs. That's because the components and devices and the requirements are constantly going up in speed. So no surprise there, I'm sure, to anyone on the webinar. So we look at the total loss of the system, and it's a combination of the dielectric conductor. A lot more about that coming up in the presentation. But generally speaking, rolled annealed copper is the go-to copper for flex because of its flex and bending properties. It also happens to be very good for high frequency. So you kind of get that benefit automatically when you're building flex. One of the things I'm going to talk a lot about today is the dielectric on a technical data sheet and what you actually use in your algorithm to figure out the line width and dielectric thicknesses to hit a target impedance. And some of it depends on how you measure the dielectric constant of these materials. It's important not to get too hung up on this. The fabricators will have history, and they'll know what dielectric constant value to plug in their algorithm to get the right target impedance. But you know, just Kapton is a lower loss material, but its decay is about the same as the acrylic adhesive. Again, I'm going to talk more about the HP, the GPL, and the TK materials and how they fit into all this. You know, dielectric constant is something that, you know, some people get wrapped up in, and my advice is, you know, go with the values that your fabricator uses to hit a target impedance.
So Chris, what if I have a need to run RF through flex? Are there any specific design considerations?
Yes, especially if it's, obviously you wouldn't want to put an RF radiating device like a Wilkinson divider in a bend area, because that will change its performance dramatically. There's actually a few cases where that's done on purpose because it's used as part of a sensing device. Not necessarily a Wilkinson divider, but some other RF circuit. But yeah, there are some special considerations. Typically RF components are done in a rigid flex in the rigid area, or on a flex in an area where there'll be a stiffener. Fortunately, again, flex using rolled annealed copper will give you typically better performance. And one of the things, not so much for RF, but one of the things that's nice about flex, especially with differential pairs, is there's no skew due to the fiberglass. There's no micro decay discontinuities. But true, yeah. I have a little bit more on RF coming up in the presentation. Okay.
Thanks, Chris.
You're welcome. So Microstrip, for those of you who are not familiar with Microstrip, that's basically where we have a reference plane and a conductor. In the case of flex, there will always be cover lay on the surface, which is not represented in the picture in the upper right. But these graphics are kind of nice because it kind of gives you the idea that the field actually runs or lives in the dielectric, and the trace is more of a waveguide. So this is kind of a nice conceptual example of what's happening. In traditional microstrip and in PCB, you have field lines running in air, and they're coupling through the air down into the reference plane. And of course, if cover lay was there, it would be partially in the cover lay and partially in air. Cover lay itself is a composite of both acrylic adhesive and the Kapton surface layer. Anyway, you always have something on top of your circuitry, even in a microstrip example. It could be solder mask, it could be cover lay. You know, rigid world, you know, that's typically solder mask. There are some advantages to a microstrip structure. Basically, because there's only one reference plane, you can run wider traces for the same target impedance. Whereas in a given thickness for strip line, you have to make the trace narrower because you're referencing two planes. And this just shows an example with the cover lay. The bottom cover lay in a structure like this is not electrically active in the circuit. So you're only dealing with the electrical effects of the base dielectric and the actual cover lay properties. And you can see, you know, in the upper right in the diagram, you have the dielectric constant of the clad, and then you have the dielectric constant of the cover lay, the height or thickness of the dielectric, the thickness of the trace, the thickness of the cover lay, and the width of the circuit. Again, these are all components that that have been tried and true and figured out by folks like Royal Flex.
Yeah, we tend to have quite a bit of history building different ones, and we'll work with the customers on stack up. Sometimes we have to, you know, recommend a few different changes. You can adjust the line widths, but sometimes you do have to adjust the dielectrics in the build itself, and that's where we use a software that helps us not only maintain what our numbers are coming out at, but to help plan for future builds in combination.
So what this chart is basically showing, I'm going to boil it down. Again, the slides will be available for further review, but basically what you can do is you can hit a target impedance with a thinner dielectric and a wider trace with a lower dielectric constant. So the lower the dielectric constant, the thinner the dielectric can be, and or the wider the trace can be, and hit the same target impedance. And that can have a lot of benefits from a signal loss standpoint. Generally speaking, wider traces provide lower loss. So if you can have a wider trace and still maintain your target impedance in a particular thickness structure, you'll get better performance.
What if I wanted to perhaps run a small 2.4 gigahertz antenna on this? That should be possible then, yeah?
Oh yeah, yes. Even with something on the lossier side like the acrylic adhesives, that's doable as long as you understand what the loss will be and you can tolerate your design. If you can't, then that's when you have to start thinking about other materials. But yeah, that's certainly possible. Again, with the rolled annealed copper, from a copper performance standpoint, you're already starting off with an advantage. Many rigid materials that normally use electroposited copper, if you need higher performance, you can use what they call VLP or VLP2 or HVLP coppers or rolled annealed. Rolled annealed will give you a step function improvement in a dielectric performance because you're improving the conductor loss. And that's a simple way to get higher performance on a rigid material. You're already getting that in most cases with Flex.
All right,
so,
thanks.
Yeah, sorry. Yeah, so this is just showing a strip line example where you're coupling the transmission line or signal trace to reference planes. I'm sure a lot of people on this webinar are already familiar with this, but I just wanted to show the structure. It's noise-free compared to the outside environment, with a couple of caveats. I'm going to talk about crosshatch ground planes later on. They have a lot of advantages. They have some disadvantages. The problem, though, with strip line in Flex is to get a target impedance without having a very, very narrow trace, which, again, remember, will increase loss, which you don't want. You have to make the dielectric thick. And we don't like thick in Flex for a number of reasons. It's a cost driver. It also decreases flexibility. So again, we're going to talk more about that when we get to crosshatch ground planes. But there are also something I'm not covering in this presentation because it probably deserves its own, is there are silver inks that can be screened on as a reference plane or shield layer in Flex. There's a product that's been around for a long time called CB028, which is a silver flake ink that can be used as a shield layer. And then, of course, there's some new products out there that are based on silver-filled polyimide systems with very high operating temperatures. And those have multiple applications. They can be used as Flex heaters. They can also be used as Flex shield layers.
And then with the silver shielding, we build quite a bit of that. We see a lot of medical products, and it's basically adding another layer, like you said, but with keeping the board much thinner and flexible, and you get the proper grounding that you need. But we do some high volume boards with that silver, and it's, you know, we're pretty good at applying that and sandwiching it between cover lays and such.
Yeah. Yeah.
How
So
effective are those versus, say, an additional just doing a copper layer on top?
copper is hard to beat, but because the silver flake particles overlap in the ink, it's pretty good.
Right.
But copper is as a shield layer. It's very effective. But you know, the trade-off happens more in a crosshatch ground plane than it does with a silver shield layer. And again, all these technologies have pluses and minuses. And, you know, that's where working with, again, I know I say this a lot, but working with the fabricator, you could get the best, you know, option for your design.
And combination sometimes.
Right. Yes.
Yeah. Products.
Thank you.
So talked a little bit about high frequency effects in copper. Again, probably not a surprise to most of the folks on this webinar. But one of the things that some people might not be aware of, even though they might be very high frequency familiar, is the effect that the foil has. And, you know, I've talked a little bit about the benefits of rolled annealed copper. Its structure and its finish are smoother, and that produces more or better transmission line. I'll give a great example. Some folks think that because of the skin effect, in other words, the current that travels in the trace moves to the surface as you go higher in frequency. That because it's rougher, the copper has to, or the energy has to travel in the surface, and it has to go through a longer distance because it's traveling through a rough surface. Really what's happening is it's acting more like a radiator in your car or radiator in your home. If you have more surface area, more of that energy is going to be pumped into the surrounding dielectric. And that's something that increases loss. So smoother trace will have better or lower loss characteristics. Really becomes a big factor above 10 gigahertz. You know, that's where the roughness of the copper becomes close to the wavelength of the signal. And just some more information about copper foils. Yes, these are all the same magnification, and you can see how rough copper can be. The foil on the upper left is something we use with rigid polyimide because that notoriously has lower adhesion. So rougher copper gives you better adhesion, but not good for high frequency or low loss. And then as you get smoother, you get better performance. Again, automatically comes with the rolled annealed copper. Just some information on copper. Most common in flex, we deal with grade 7 and 8. And what happens is when you process flex materials, grade 8 becomes grade 7. In other words, it has all the properties of grade 7 with regular PCB processing. In fact, a lot of that happens in the manufacture of the dielectric clad material itself. But these are types of foils. Yes, number 4 is missing on purpose. It was an older designation that has since been deleted. And actually number 6 had been deleted and then brought back. And again, number 6 will become more like number 7 with processing. So I talked a lot about trace width and thickness, and generally speaking, more copper gives you better high frequency transmission properties. And there are ways you can get performance by using a lower decay cover lay. And again, the point here is that if the dielectric constant's lower, you can have a wider trace and better high frequency transmission properties. TK laminate is a Teflon Kapton composite. It does require high temperature lamination. We do have a new product called GPL, which has closer dielectric properties, both in decay and loss to the Teflon, but only requires standard lamination. So it's something we're pretty excited about. Again, where these slides will be made available in case anybody wants to go into some of these details. Differential pairs, very common in rigid designs. both in microstrip and stripline technologies. So I'm sure, again, a lot of folks are very familiar with these. It's a way to minimize crosstalk. And again, stripline constructions where you use a crosshatch ground plane. There is a frequency limitation because of the crosshatch. I'm going to cover that in some future slides. You know, these are just some good examples of some of the very common circuits we see, especially in rigid flex. Differential stripline with differential pairs and stripline, we see that very common structure in rigid flex is to have a 3-layer flex area where you have your reference planes on both sides, cover lay on top of the reference plane, and then the signal traces inside, the differential pairs inside. And you'll have a cover lay on top, but the cover lay is not electrically active in a situation like that because it's outside of the reference planes. So just some examples of eye diagrams. Don't know if everyone on this webinar is familiar with these, but basically you pump a test signal in, digital signal into your transmission lines, and you read the signal on the output side, and you look at the loss. And as the dielectric material absorbs some of this signal energy, the rise time increases and then the eye closes in, and that could be a problem at certain frequencies. And you can see FR4 with cover lay on the left and Pyralux TK. So basically the same structure, lower loss material, the eye stays open.
So Chris, has anybody that you're aware of run, say, PAM4, you know, some of these crazy 56 and 112 gigabits per second through this?
You know, I'm not familiar with any PAM4 flex circuits. I know PAM4 is something that's being looked at a lot in the rigid world. I'm sure it will happen in flex. I don't know, Mark, does it make sense to just describe briefly what PAM4 is?
Sure. So for those of you who aren't familiar, what we're looking at right now is basically 2 logic levels. Pulse amplitude modulation, 2 levels. PAM4 adds an additional 2 levels. So instead of 0 and 1 being logic low and logic high, you've got 0, say 0.33, 0.66, and 1 all at the same time. 4 different logic levels, so you're transmitting twice the amount of information without increasing your transmission frequency.
And when you have those steps in the logic levels, your noise margin's even smaller because if you have noise or loss, right, it becomes a much bigger percentage of each step. So so even the noise that would be tolerated in a standard 2-bit digital signal in the PAM4, you know, that would not be acceptable.
Thanks, Chris.
Yeah, no, that's a good point. So just general guidelines on the materials, and I covered a little bit of this already. You want to use the adhesiveless clads wherever possible. There are some legacy designs that call for the acrylic adhesive-based clads, but typically the fabricators, for good reason, don't like those for plated through holes. Again, I'll talk a little bit more about that coming up. The pure polyimide systems plate a lot more like rigid materials. So from a plating standpoint, desmear, and all the different things they have to do to make the electrical interconnects in a flex circuit, AP and AG and AC, they work a lot more like the rigid materials. That said, you want to use the acrylic for the flex areas. It's cost effective, it's widely available, well understood, very flexible. It passes the NASA low outgas test. It's good in cryogenic temperatures. It's got a lot of upside. It is lossier than the polyimide films, and it does have some temperature limitations. So there are limitations to the acrylic, but for general applications, it is the go-to adhesive building block for flex circuits. When not to use acrylic, when you need really low loss or you have high operating temperatures, those are some examples of why you wouldn't use acrylic. By the way, the acrylic adhesives actually work well in automotive fluids, and we have data on that. So things like transmission fluid and motor oil and gasoline, we have data on that. So if there's questions, feel free to reach out.
And one of the things we find with the acrylics is, especially in the rigid flex, we remove acrylic, even though it's in the product, from anything that has a thermal area. So anything you're going to be assembling and that, we try to use a combination of materials. So even if it's a pure flex job where we're using an LF bond ply, if you're going to be doing lots of assembly and you're probably going to put a stiffener behind it, we're not necessarily going to be using rigid cores, but in that selective area, we'll put pre-preg and we'll cut back the adhesive. That way you still get flexibility everywhere you need it. And in the area you're doing your soldering and your through holes, you can still get a real robust Z-axis control there without having separation, because LF, when a heat's applied directly in assembly, you sometimes can get separation in the whole wall at the higher temperature. So that's one of the little tricks we can use and still keep it a pretty simple 3-layer flex or 4-layer flex.
Or Chris, I'm sorry, what's a good maximum temperature for these acrylic adhesives, do you think?
So its rated operating temperature is 105 Celsius. I've known people to use it up to 125 in continuous operating conditions, not a problem. Its decomp is 315 Celsius. So the decomp is pretty high. What happens with the acrylic adhesive is it will soften at the higher temperatures, but as soon as it's cooled, it goes down to its normal condition. Where you run into trouble, or where you can run into trouble, is when the material is mechanically stressed during the high temperature point where it's soft. So if the material is flexed or bent when it's, let's just say 150 or 200 degrees Celsius, it won't be decomposing, but it will be very, very soft and very vulnerable. Now, when it cools down, it goes back to normal and no harm's done. But if you have any separation or any other issues while it's at the higher temperature, you've got a problem. So those are some of the limitations with the acrylic. By the way, I just want to point out, we use LFFR. Those are two types of acrylic adhesives. And acrylic, we use those terms interchangeably. So if there's any confusion there, I apologize, and certainly don't hesitate to raise your hand if you have questions about that. The LF is a legacy product. It's still very applicable today, but not for every application. The FR is the same base polymer with a flame retardant system added. So if you need V0 UL flame rating, you would use the FR. If you don't, then it's very common to use the LF. The LF is also clear. And I've actually participated in some applications where the LF was used by itself without the polyimide, where you needed a clear bonding material. And it's got some interesting properties, but not for everything. Again, that's where we want to come and help and say, yes, this is a good application for acrylic. Oh, no, you might want to consider pre-preg, or you might want to consider HT or GPL. And of course, rolled annealed copper is the most common copper. Just going back to generalizations for flex, rolled annealed copper is the most common copper used in flex applications. There is some limitations in how thin you can go. So there are some, especially in medical devices, there's some applications where you want very, very narrow circuits, and you want to start with thinner foils. There is a limitation. Basically 9 micron, which is relatively new, is the bottom end of rolled annealed. And that's because of improvements in manufacturing processes. Thicker coppers are easier to manufacture because you can imagine you're rolling this down to a particular thickness. And then electrodeposited foils for the ultra thin foils. So looking at the low loss and high speed part of this, as you can see from here, the acrylic adhesive, these are the DF factors or loss tangent dissipation factors for the different materials. You see the acrylic is lossy. Doesn't mean you can't use it at, for example, 2.5 gig. Just be aware that, your loss is going to be higher than if you use some of the other materials. It really depends a lot on the design. The standard materials like AP and AG outperform many of the rigid PCB materials. So if people are familiar with things like Rogers and Megtron 6 and Itera MT40, those are very low loss materials used in high-speed rigid PCBs. AP is already there. It's already in the same loss group as those materials and has been for a long, long time. In fact, I've seen applications where AP is used in rigid boards, both to manage skew and to get lower loss characteristics. And it's also a lower dielectric constant. So these materials, AP and AG, already outperform many rigid materials that are out there.
To touch on that, Chris, yeah, we've built a number of multi-layers using AP as the base laminate, and the goal is to keep it a little thinner in the the higher layer stack. So it's a little different build, but it's we've done a number of them that way, and then a lot of times it's so they can put more layers in a little tighter package, right? Because
so basically it's a great segue into Intera, which is a buried capacitance material, is used not so much to generate capacitance, but to lower the in-plane inductance, and then you can get rid of the surface caps because you can have it very thin, and it holds 5,000 volts per mil, so you don't need a high thickness. And in the case of stripline or microstrip constructions, because it's a lower dielectric constant than many rigid materials. FR4, its decay is somewhere between 4 and 4.5. The AP is more like 3. You can have wider traces or thinner dielectrics and maintain your impedance. Yeah. The GPL is a new product, which I'm pretty excited about because it allows for low loss structures with conventional lamination. The HT has, I think, a ton of application, ton of possibilities, both to replace high temperature cabling, but also in low loss environments. And actually medical applications, because you could autoclave a TK structure repeatedly and not have to worry about the circuit degrading. And then, of course, the TK bond ply, very low loss, very low dielectric constant. So all these materials have applications. And, you guys have all heard Bob talk about some of the things that they've done at Royal Circuits. These guys know the materials. We work very closely with them. And again, the goal is to get your design successful early on rather than having to go through, several iterations. So one of the things I talked about was the Pyralux TK, and it's basically a Teflon Kapton laminate. So if you look at some of the Rogers materials where you have a PTFE or Teflon type fluoropolymer dielectric, it's very often reinforced with fiberglass, which takes away from its properties, but you have to have it there. I don't know if anyone's ever handled Skype Teflon. We use it as a release film in manufacturing. It actually has good electrical properties, but you can't really make a PCB out of it for a lot of different reasons. Copper doesn't stick to it well. It has poor dimensional properties. It's just a big challenge. So they put fiberglass in it to make it a viable PCB material, but then that glass takes away from its performance. In the case of TK, the Kapton layer acts like the fiberglass. It's providing XY stability to the Teflon material, and it doesn't have the drawbacks of fiberglass. So it has very interesting low loss properties for high-speed circuitry. If you use the bond sheet, the TK bond sheet, which is also a Teflon Kapton composite, to make a multi-layer circuit, it does require high temperature lamination. One of the options is use the GPL adhesive in making a TK structure. So you have a hybrid structure of the Teflon Kapton and the new GPL low loss adhesive. You'll be giving up some performance, but it's going to be way better than the standard materials, and it's conventional lamination. I've talked a little bit about the HT material. Again, I think this material has all kinds of applications, everything from automotive under hood, aircraft, and of course, medical applications. And I talked about this last week. I've taken some HT circuits and I've floated them in solder for an hour at 550 Fahrenheit, and it just doesn't do anything. It doesn't bother the material at all. So it's a very high temperature material. Exceeds most, if not all, organic PCB materials in operating temperature. The only thing that goes beyond the TK, or sorry, the HT is ceramics. So it's a very interesting material, both low loss characteristics and high temperature characteristics. It allows you to make 100% polyimide structure for flex. LCP is something that people were very excited about because of its performance characteristics, but LCP cold work, that, by the way, that's liquid crystal polymer. That material cold works, and you can develop stress cracks if it's bent repeatedly. These films don't suffer that particular characteristic. As Bob mentioned, with acrylic, you typically keep that out of the rigid portion, so the thermal areas, the plate through holes, don't go through the acrylic. That limitation is not true with HT film. You can run the HT film all the way through the structure. And just some examples of HT structures as it's laminated. You can see it's a very uniform dielectric system with low loss characteristics. And this just shows some loss tangent charts with HT versus standard LF. And you see the LF in both cases. You're dealing with polyimide cores, but in one case the adhesive component to build the structure is the acrylic versus the HT. Very good the signal performance characteristics. So it have application in high-speed transmission lines in a rigid flex as well as RF structures. So now we're getting into some of the mechanicals of flex. And I see we're kind of running a little bit long on time, so I'm going to go through these pretty quickly so we have some time for questions and answers. Again, I know I've said this many times in this presentation. This is where the Royal Flex folks can help. General guidelines for bend radiuses has to do with the thickness ratio of the circuit to the bend radius. Of course, there are lots of caveats to this, and there are some ways to improve it, like putting the circuitry in the neutral axis. But basically, when you bend a circuit or bend any material, the outside of the bend gets stretched and the inside gets compressed. And there are ways to mitigate this, both with bend radius and with the structure. Just some general guidelines. Again, we'll make these slides available. If you have a single plane layer, try and keep it near the center of the bend area or the stack up. So in this example, you'd want it in the middle, which is seen here. So you have a thicker cover lay here versus a thinner out here. Use loose leaf constructions for multi-layer flex. That means that the individual flex layers in a multi-layer flex and a rigid flex are not bonded. Obviously, you keep PTA plated through holes out of those areas. You don't want to have traces running in different directions in the flex area, and avoid I-beam constructions. And use crosshatch planes where available. And I'll talk a little bit more about that when we get to that section. But here's an example of the loose leaf construction where you have these different flex areas and there's no bonding in here. So that allows these areas to move freely and much better. In fact, in what we call bookbinder system, you'll actually have different lengths of these rigid flex, or sorry, these flex portions in the rigid flex. So if this is going to be the convex area in the bend, this circuit will be built where this section is longer than, for instance, the one that's inside. So this one doesn't have to stretch and this one doesn't have to compress. Just a great example of where the cover lay is cut out in the rigid area. So if I'm going to bond the rigid materials here and here, the cover lay only extends in about 50 mils. And that's to keep the cover lay and the acrylic material out of the plated through holes and out of the thermal areas. Just some circuit design. Again, something that the Royal Flex folks can help with. To get a more robust design, you wouldn't terminate your trace at your pad like this. You would have what we call a fillet, and you can see some examples of the fillet on the the lower right picture. And of course, Ecobond fillets are used in rigid flex transition areas, very commonly used, and it's a great way to prevent that stress area being at a hard bend where the actual rigid material can cut into the flex circuit.
Yeah, and on a double-sided flex with a stiffener, sometimes you're showing that now, where you have a hard bend that you may want the Ecobond along that stiffener as well. Keep it from separating.
Do we do that on dynamic flex or just bend to install or both?
Usually bend to install, I would think most of the time, right, Chris? Because usually rigid flex aren't dynamic in general. They're not using them that way.
Right. It's unusual to have a rigid flex that's dynamic, but you know, bend radius and you know, and other things would also drive the need for using Ecobond fillet. It's almost always a good idea to use that. It's just it's cheap, and what we call cheap insurance. So one of the things you can do too with a flex circuit is you can have these tear stops. The other thing you want to do too is not have any areas where you could have stress built up in a system. So you would want to have curved radiuses instead of 90-degree angles. And any transition in size. One of the things I do want to talk about, for those not familiar with flex fab, is something called button plating. Very important in flex. The rolled annealed copper has a very good structure for bending, especially when the grain of the copper is oriented correctly. You don't want to put electrolytic copper on there, and in fact, it's even more important not to put things like electroless nickel there. Electroless nickel builds up in nucleation sites, and then you have these grain boundaries, and I have an image on the lower left. If you bend that structure, it'll crack and then transfer the crack into the copper trace underneath. Once again, you know, the folks that build these circuits would definitely steer you away from having to put the metal plating in those areas. Totally fine to put it on pads and surface mount lands where there's going to be no bending, but you want to keep that out of the flex areas, and you want to keep that off the traces that travel in a flex transition zone. We talked about this already a little bit, but the I-beam effect, you really want to keep the, and it's also a benefit from image transfer as well, but you want to keep the circuit staggered like you see on the right-hand side.
Chris, I've got a quick question regarding those tear stops, and a lot of people have popped this one up. What are they made of?
It's the copper. So when you image your circuitry, you're imaging in the tear stops.
So you just put down a floating copper trace?
Yeah, feature, yeah.
Interesting.
Yep. Yeah.
Okay.
So from a process standpoint, it really doesn't require any extra processing. You just need to put the tear stop into your image, into your layer, circuit layer.
Okay, and let me make a quick announcement for those of you who might have to leave at this point. This presentation is being recorded and will be made available at royalcircuits.com/blog-2020 within 2 business days. We're going to keep rolling with Chris and Bob, and I still have your questions, some of your questions to answer. We will get to those. There's not that many of them. All right, after you, gentlemen.
So we left off the I-beams. Yeah, so you can see where the I-beam effect would concentrate the force in a bend, and that's why you would stagger the circuits. Going back to crosshatch, I know I talked a lot about that. Very, very important. Crosshatch is a great way to get better flexibility and better survivability in assembly, but it does have its caveats. There is frequency limited. When you get to a certain frequency, it doesn't work as well. It's not as effective as a shield layer, but it does have a lot of advantages because you can get the same impedance in a thinner package with the crosshatch planes. You greatly improve the flexibility on top of the fact that a crosshatch layer is more flexible than a solid layer. So there's benefits to that, but there, you know, it's not for all cases. There's a very good HD Pug study on this that DuPont participated in. You can find that. It was presented publicly at IPC a few years back. You can find that presentation. If anyone has trouble finding that, I can help. But it's also a moisture egress, very, very, very beneficial for assembly. When you bake your flex circuits prior to assembly, which I always recommend people do, this allows for moisture egress. Part of the HD Pug study was that round openings were better for high frequency, and they were just as effective for flexing and moisture egress. So these are just some of the parameters around that study. But I recommend these whenever possible. It's just a better circuit, you know, unless you're at very high frequencies. And this just shows some of the strip line insertion loft cutoff frequencies where the loss increases and you're more susceptible to some outside influences. And the frequencies are quite high. Again, more detail on this in that HD Pug study. But whenever possible, definitely recommend using the crosshatch planes for both assembly and flexibility, and even design stack up. It allows you, again, to get a higher impedance in a thinner package. Just a note that there is something called Pyralux APR. It's not an inexpensive material, but it's a technology that exists. Again, probably we'll see more use as circuits become more complicated. But basically, it's a nichrome layer that's deposited on the backside of the copper foil. And the foil is laminated down to the dielectric, the polyimide dielectric, with the nichrome layer facing or touching the dielectric. And then you can selectively etch. So you etch your copper, you come back and you etch away the nichrome, and then you come back and etch away copper to reveal the nichrome, where you only have that bridging your copper circuitry, and that becomes your resistor. Interesting technology. It's used in rigid as well as flex, but it's just a quick introduction into this technology. APR is available. So we're wrapping up. I know I went through some of the slides pretty quickly to try and keep us in the hour. Flex is growing. We see all kinds of applications for flex growing, especially in the medical areas. It's always been a part of aerospace and outer space, where it's finding more uses in automotive and medical, especially with vehicle electrification. I think we're going to see a combination of printed electronics and more traditional Pyralux or Kapton polyimide-based circuitry in automotive. But there's a ton of medical applications, both surgical and in things like drug delivery and sensors, all kinds of applications there. Of course, speeds and low loss needs are increasing with both RF and high-speed digital. And then, you know, many applications for electronics are possible. You know, with the Internet of Things, we're seeing electronics pop up in areas that weren't previously electrified. And then the new materials, AG, GPL, HT, etc. You know, let us know what your challenges are, and we'll find the material to help solve those issues.
All right. Well,
just want to give a shout out to the Royal Flex team and DuPont Electronic Solutions, Del Smith. They provided me with a lot of the images and data. So thanks to those folks. And then we're ready for questions.
All right, Chris, thank you so much. And Bob, thank you so much for your knowledge today. We do have a few specific questions. And if you have more, please feel free to ask them. Now's the time, because we're going to wrap up here pretty quickly once these are done. First question is related to stack up your drill files. How do I specify the hole sizes in the stiffeners? And here's the complete question. When adding a stiffener with through holes for components, I might want the hole in the stiffener to be as big as the copper pad rather than the hole that goes through the flex. Do I need to supply 2 drill files? Or can I just supply a Gerber file showing the cover layout line with pads to mark the holes the size I want the holes?
Either way would work as marked. You don't have to show it as separate, but if you show your stiffener Gerber file with the the diameter you want, we're going to convert that to a drill file. So as long as you identify it clearly, we can just simply use a layer to generate that from. So that's pretty common.
Okay. We also had a question that I took the liberty of typing an answer to, and that was, at what point should I start interacting with the Royal Flex team to work on my stack up? At the beginning of the design process or towards the end?
Either way, depending on where you're at in the design process, to overcome if you have questions regarding, a form and fit. If thickness is a big issue and you're how many layers you're trying to put in. But we would assist you at both times, to be honest with you. If you want to come in and get some initial information, work on your design and come back. That's something that's pretty common with a lot of our customers. We're doing that on probably a daily basis. So if you want to reach out when you're looking at your initial design to get some questions, and then as you're putting it together, it's pretty common that we'll have 1 or 2 meetings with the CAM and the designers to make an effective stock up for you.
Slow your roll there, Bob. That sounds expensive. How much does that kind of stuff cost?
Yeah, but usually they're fairly quick. I mean, we don't charge for that. We just, want an opportunity to get the quote and get, usually by then we're pretty intimate with the design. So generally we're going to see the part anyways, because they want to, not want to re-explain it to another manufacturer. So we make our services available through Ricky, our salesperson, and we have multiple planners and CAM operators that we try to get on that pretty quick. And help you get your design off the floor. I mean, we'll have a conference call with 3 or 4 people generally if we need to, and go through, what can lay out your board if you have to make changes, especially if we get your design and say, hey, we need to make some changes with you, then we're going to put a lot of effort into getting something that'll work for you.
So I just call up and all that's free.
Yep.
Wow. That's great. Okay, now on to some technical boards. Process question. If I have 2 boards connected by flex, can I have different stack ups for each of the rigid boards?
Yes, we do that. We generally don't like seeing 2 total different thicknesses because that creates some press difficulties, but we've built rigid flexes where literally they have a 30 mil rigid on one end and a 60 mil on the other. So when it comes to rigid flex, a lot of it is how we look at it is what we remove for the flex areas. So that'll stay the same, but if you have a different core thickness, if it's on the same layer, we've actually on the same level, we've done that before, because with rigid flex, you're putting it together in pieces anyway. So instead of just routing out a pocket where the flex is, we'll actually, cut half the material, one end and use say a 20 core. And then at the other end, we've used a 10 core, and they're both layered, say layer 2, 3 or something like that. And we've done that before. That's a more intricate build, and it definitely will be more pricey because we're going to have to build setup and tooling plates so we can press evenly when it goes into the final press. But that's something that we've done on a few occasions, but it's not more common is having different flex arms at different layers. So you'll have areas that might have flex layer 2, 3 going across, and then even though layer 4 and 5 might be flex, it may not go through this opening. It might be a different flex area. We'll have layer 4, 5 going across to the different ridges. So that's what we see more often, and it's for flexibility. And then we can remove we'll route out the flex just like we would the rigid in the areas that flex layer isn't needed. So that's more common than having different thicknesses in the rigid.
How interesting. All right. Here's a question I think might be for Chris. And this is going back a little ways in the presentation. So the question is, thicker copper is not necessarily low loss considering skin depth might limit effective copper being used. Is this understanding correct? So the question, it looks to be, is is the heavier copper lower loss?
Generally, yes. The more copper you have in either dimension, either in width or in height, it can be. And the only reason why I'm saying there's a caveat is because thicker copper will have more sideways coupling. That's probably something better addressed in a whole separate presentation. But generally, thicker copper would be lower loss. You know, I would say generally it depends on some of the other things that are going on. But all things being equal, a more copper trace, either wider or thicker, will give you lower loss because you have more surface area.
Okay, thank you so much. And we'll close that one. Question relating to EU RoHS directive. Are there any concerns about future additional materials added to EU RoHS directive affecting efficiency of designs?
That's a good question. That's a little bit complex. Fortunately, the polyimide films do not contain flame retardants. Because of their high temperature characteristics, they already passed the UL flame testing to be V0. So there are no RoHS chemistries or likely to be RoHS chemistries involved in the clads. The FR, the acrylic version with the flame retardant, could be an issue in the future because it contains bromine and antimony as the flame retardants. LF is probably not going to be a concern. GPL was developed with RoHS in mind, so that's not a concern. HT, again, high temperature polyimide, no flame retardants added. So Flex is probably in a better position overall than rigid materials in terms of potential components being flagged as RoHS restricted. So in general, I think you're going to be fine going forward, you know, down the road.
Okay, thank you, Chris. What is the maximum operating temperature for HT Flex PCB?
200 Celsius, which is very hot.
Yeah, wouldn't we have trouble with the solder changing phase? Most solders changing phase at that temperature?
Well, that's a great point. Actually, the decomposition temperature of HT, NAP, and AG are in excess of 500 degrees Celsius. Probably more like 540, 560 Celsius. What limits the HT operating temperature isn't the polymer, it's actually the copper foil. So yeah, there are challenges for solder at those high operating temperatures, and that's something that needs to be considered. There are solders and also something called Ormet paste that have higher operating temperatures than standard SAC 305. Again, probably could be a whole presentation on its own or webinar on its own, and getting into some of the high temperature characteristics. But yeah, certainly at a 200 degree operating temperature, you need to start thinking about the interconnect metallurgy. It's a great point. Great point for a question. Yeah.
Thanks. Okay. Specific question for Chris. Which foil grade is best to use for 10 gigabit per second low voltage differential signaling?
Definitely, I would pick rolled annealed. You could use electrodeposited with what they call a VLP or HVLP structure, where it's very smooth. But you wouldn't want to use those foils in flex anyway. So if it's rigid, use the HVLP or VLP2 foils, very low profile. By the way, that's what VLP stands for. For flex, stick with rolled annealed. It's going to perform very well at those speeds.
All right, thank you. Another last question, and I might have to take this one unless you want to give it a shot, Chris. Is there any guidance for calculating DC resistance and thermal conductance of crosshatches?
That's interesting. Yeah, I'm going to let you take that one, Mark. I will just add that usually that's not an issue because there's enough copper mass there to not cause a DC resistance issue. But go ahead, Mark, please.
Sure. Yeah. So what I would say, Steve, if it really is a concern for you, and can't imagine at DC levels that it might be, but if it is, you're probably going to want to use finite element analysis, or at the very least, just generate a unit cell, a repeating pattern that you can go through and analyze. Thermal conductance of the crosshatches. Copper is a really, really good conductor. It's, you know, north of, what is it, 420 watts per meter Kelvin, something like that.
It's in the 400s, yeah, watts per meter Kelvin.
I mean, it's pretty high. You're not really going to have much trouble in terms of conductance. But the book that I would recommend is by Doctors Brooks and Johnson. They went through a whole analysis of trace temperatures on printed circuit boards. They might have some interesting things, not necessarily on the crosshatch, but more on the strip lines themselves. But finite element analysis, if there's going to be any conductive effects, you know, at that point you need some computational fluid dynamics. But, you know, if it's that critical, I would simulate it rather than estimating it. We also have a great suggestion here by Fred, and he said a good approximation for the DC resistance and thermal resistance might just be percent area of the copper. You know, if you're removing 10% of the copper for thing, derate it by that much. I think that's a great suggestion, Fred.
That's a great suggestion. Keep it simple, right?
Yeah, I mean, God, yeah, that makes it easy.
Yeah.
But I'm kind of with you. I can't imagine. I don't know what the application is, but I can't imagine it would be a concern. I'm not saying it's not. I'm just saying it's got to be an interesting application for that to be the case. So,
yeah, just a side note: polyimide and all dielectrics are poor thermal conductors. You can add things to improve their thermal conductance, fillers, and the like. But one of the nice things about polyimide films is they perform very well in thinner structures than corresponding rigid materials. So you get the same performance both in dielectric strength and as in dielectric constant. And when you make material thinner, its thermal resistance goes down. So so you can get good thermal performance out of flex films just because you can make them thin.
Okay, one last question. So the rule of thumb is that you need to worry about surface roughness at what frequency?
It plays a bigger role above 10 gig. So, and that's because the roughness of standard foils, you know, approach the wavelength of the material.
Okay.
So, or the copper, I should say. Yeah.
All right. Well, with that, I would like to thank everybody who attended for hanging in. I do realize we went a few minutes over. I appreciate your staying with us. This presentation has been recorded and it will be made available at the royalcircuits.com blog page within the next 2 business days. This presentation was hosted by Royal Circuit Solutions of California and Advanced Assembly of Aurora, Colorado. Chris Hunrath is with Insulectro, and if you have any material science needs, I've yet to find his equal in this industry. He's a great guy to have around. If you have any circuit construction needs, Bob has, oh gosh, Bob, is it 4 decades of experience now?
Yeah. Yeah, remind me. Yeah.
Hey, I mean, I don't want to bring up that you've been making boards longer than I've been alive, so I'm not going to do it.
Okay.
But I love having you guys here. Please feel free to reach out to Ricky at Royal Flex Circuits. And if you have any other questions, reach out anytime. We'd love to have you. Thanks so much, everyone. Have a great rest of the day and join us next Tech Talk Teach Thursday. We're doing these every week at this point. Take care. Bye.
All right. Hey, Chris.